Swayam Prabha. Digital India. Educated India.
So let's look at the part which we had discussed last time, which is the system topology part and the impact of it, right? So I already talked to you about the GPU. We ran NVIDIA SMI. We saw there are 8. I talked to you about the concept of peer-to-peer transfer, and in case I don't have it, what happens? So in case GPU 0 and GPU 1 do not use memory lanes like NVLink, and they are not directly connected in the system, in that case, if there is a host staging which happens, which means from GPU, it goes to the CPU, and then from CPU, it goes back to the GPU 1, that is going to reduce your throughput and increase the latency, reducing your overall scaling. In a peer-to-peer transfer environment, you should be able to directly talk between the two GPU, and you don't need to do a hop from the CPU. Now, the question that you might have is, how do I know this? Now, already GPU provides you tool to do that. So here I'm running a command called as NVIDIA SMI topo-m. Topo stands for topology, M stands for matrix. So I'm telling it to tell me more details about my system and how those GPUs are connected to each other. So in the system where I'm currently, as you can see here, GPU 0 is connected to GPU 1 via NV1, while GPU 0 is connected to GPU 3 via NV2, right? So, and you can see here, what are the definitions of NV? NV is the connection traversing a bonded set of number of NV links, right? So how many NV links you are actually traversing it through? To give you an example of of the topology which we showed last time in the DGX, if you can see here, GPU 0 and GPU 1 is connected via one NV link, so hence NV1. But if I look at GPU 0 and GPU 3, they are connected to each other via two NV links, which means if one NV link is giving me a speed of 25 Gbps between GPU 0 and GPU 1, at the same time between GPU 0 and GPU 3, I have two NV links practically giving me 50 Gbps. So it is increasing my transfers between these two GPUs. While when I go from GPU 0 to GPU 5, I don't even have an NV link. So I'm going to take a path of force staging, right? And that's what is kind of replicated here. From GPU 0 to GPU 1 and 2, I have one NV link. But when I go to GPU 3, I have two NV links attached, which is very good because I basically get more speed. The more number of links of NV link, the better it is for me. But if I look at GPU 5, I said that there is no NV link connection and we are going via system. What is the definition of system? The system is I have to traverse via PCI as well as between the NUMA nodes. Here there are two NUMA nodes, CPU 0 and CPU 1. And I have to traverse from GPU 0 to CPU and then transfer to the next NUMA node, which is CPU 1, and then come back to GPU 5. So the interconnect between 0 and 5 is kind of weakened here, right? And for different systems, you will see a different topology. And based on this topology, you will see different scaling numbers when you use multiple GPUs on the system. And if you want to go across, again, you would see that there are InfiniBand or Mellanox switches which are there. So GPU 0 and Mellanox switch is connected via PIX and PHP, while the Mellanox switch 5.2 is going again via system, which means if GPU 0 wanted to transfer its data to another node, which is not shown here, to another node, and if it was using this NIC card, again it will transfer to the CPU. From CPU 0 it will come to CPU 1, and then it will go via NIC to the another machine, which is again not a very good scenario. Now this kind of gives you the overall topology of your system. So whichever system you run it on, you would be able to see the topology for your own system. So as I said, you can basically think of it like this, that you can have multiple connections and each and every connection will have a particular thing. Like NVLink 2 is going to have very high bandwidth and low latency. NVLink 1 will have a very high bandwidth, higher than the PCIe, but it will be lower than NV2, right? But the latency will be still low. So based on what bridge or what topology is there on your system, you will end up seeing a different chart of bandwidth and latency. Idea is to have higher bandwidth and lower latency to have better scaling results. Okay, so you can see here some of the numbers which are there. Like for PCI, it gives you maximum 15 Gbps on a PCI Gen 3, right? And while the NVLink, you can go up to 50 Gbps, right? If you have a double NVLink, you can go up to 100 Gbps or bidirectional bandwidth. So you can see the differences when you have a system with NVLink and without a NVLink. Now, how does it matter is something that we are going to see here in this particular section when we are talking about performance variations. So again, we are going to do the same thing previously, but I'm going to enable more information about the communication using NCCL. So you can see here, I'm setting the NCCL flag debug so that I can get more information about the way I'm transferring the data behind the scenes using NCCL. So even though I'm using TensorFlow and I'm using HoroWorld as the framework, I am still going to utilize NCCL as I told behind the scenes, but this flag will help me in identifying when I do communication between 0 and 3 in a multi-GPU environment, am I using NVLink or am I not using NVLink, and what kind of a numbers I can expect. So just give it a couple of seconds and we should be running. So you can see here, it has started giving me more information. The first thing it is telling me is that I've started using NCCL. What is NCCL and all, we'll talk about it in a bit, but NCCL is something which I'm using and it gives me information. Like it is telling me that for NCCL between 1 to 0, between GPU 1 to GPU 0, which is the 0 and 3 GPU, I'm using peer-to-peer communication. I'm using peer-to-peer communication, right? It states it when you are actually enabling the flag of the debug info for NCCL. And by the end of it, you will get certain number of images per second. Here it is around 1,50,000 and 98 images per second. So again, we are running a fashion MNIST only on 2 GPUs here. The same thing now, what we are doing is instead of doing it via 0 and 3, I'm going to use GPU 1 and 7. And if you remember earlier, 1 and 7, if you see 1 and 7 here, they are not connected directly via any kind of NVLink, right? So let us see what does NCCL tell us when it is trying to communicate via the between GPU 1 and GPU 7 for the same exercise which we did earlier when we got 1,50,000, right, some number. So instead of showing that between 0 and 1, I'm using peer-to-peer. Now, as you can see here, it is stating that I'm using something called as a shared memory, and I am not going via peer-to-peer. So it is stating that I don't have any direct link between these two GPUs, and hence I'm going to revert to using certain sort of shared where I have to transfer the data, say via host staging if required. And you can see here that my images per second has reduced from 1 lakh something to 94,000. So by having NVLink versus not having NVLink, you can see here that the number of images per second that I could process has in fact reduced, right? So this is what we can see. So again, repeating, we enabled a particular flag. So I'm running using HoroWorld. I'm running on 2 GPUs, but I decided to use GPUs where I knew there is a NVLink connection versus there is no NVLink connection. I'm running it for fashion MNIST, and I enabled a particular flag called as NCCL debug info, so that I can see what NCCL library behind the scene is choosing when I start communicating across the two GPUs and the impact of it as well, right? Now you might again start talking like, okay, this is good, but I will also introduce you to tools which you can use for actually finding out more details of how well your model was actually running on a GPU. So NVIDIA has a tool, which is again a free tool which you can use, which is called a DLProf, Deep Learning Profiler. Now DLProf is the one which will give you more information about when you run your model across the GPUs, how well you are utilizing the GPU. So NVIDIA Deep Learning Profiler is a tool which is built specifically for data scientists to understand and improve the performance of their model. So you can see here it is built obviously over the NVIDIA computing platform. It runs in a container environment, and it can run on different NVTX plugins for TensorFlow, PyTorch and all. And it basically is built over the Nsight system itself. And we are going to see a demo of it. So we ran this session earlier, but let us try to run it once more. In this particular case, you can see here, I am using a tool called a DLProf, and that DLProf, I am giving it certain parameters, like I am telling it that I'm going to run the DLProf, the profiling, and I want to gather the TensorFlow statistics for distributing the work, and we'll go back to the theory in a bit. Like TensorFlow has its own way of distributing the work. The TensorFlow uses an API called as Distribute API. And in this Distribute API, you can choose different things, and there are different strategies. Like you can choose synchronous communication, asynchronous communication. You can also choose the platform. It can run on multiple types of distribution. Like you can run it on a pure CPU nodes across, or you can also do it on Google TPU also, or you can do it on the GPU. You have to define the strategy for, say, a TensorFlow version. In the TensorFlow, if you choose mirrored strategy for distributing the work, it will basically indicate that you're going to use synchronous distributed training on multiple GPUs, but on a single machine, which means you're going to run or distribute the work across multiple GPUs, but within the same machine. It will not go across different nodes. What it does, it actually creates one replica per GPU. So you can see here it is kind of doing data parallelism, and each variable in the model is mirrored, right? And they're kept in sync because this is a synchronous programming environment. Multi-worker mirror strategy is the same, very similar to mirrored strategy above, but you have multiple workers, each potentially having multiple GPUs. So it's almost similar to the mirror strategy, and it only works within the same node, but you're going to have more number of workers targeting multiple GPUs. You also have central storage, which again does synchronous training, but there's a difference. In this case, all the variables are not mirrored across different GPUs. Instead, they are all kept on the CPU. So the CPU will have the variables, and whenever GPU go through or update the go through the forward propagation and back propagation, and they calculate the gradient, they basically communicate and update the CPU version of it, which is then taken by the other GPUs as well. So it's a slightly different environment. Where are you keeping your final state of the variable for communication is different in mirror strategy and central storage. You can also take parameter server strategy, which we talked some time back, right? Parameter server is a common data parallel method to scale up the model training. It is basically working on the concept of a synchronous program, where a parameter server training cluster, it consists of multiple workers and parameter servers. The variables are actually kept on a parameter server, and they are read and updated by each and every worker. So each and every worker doesn't need to talk to each other. They just talk to the parameter server as well. And you can also define other kinds of strategy like one device strategy also, right? So if you were to use TensorFlow mirrored strategy, in that particular case, you would have tf.distribute the mirror strategy dot scope. So that you are saying tf dot distribute dot mirror strategy, and you create the model. Whenever you are creating the model creation happens within the scope of that strategy. So you can see here you are saying with strategy dot scope, and inside that you are defining your model. So the model is defined inside the scope of the strategy that you have defined. So that's how the work of the TensorFlow works. So luckily my machine is kind of up, and let me just try to do the Docker run now so that my machine brings up again, hopefully. So it's running the Jupyter Notebook and container. If my network is stable, I should be able to bring you all back to the same tab here. Yes. So we are in the DLProf lab only, and I was taking you through the process of creating this report. So as I said, just to come back, we have the DLProf, which is the profiler running. I'm telling it to use the TensorFlow, and I'm telling it to collect it for certain duration, right? And this will give me more details about my overall thing. So in the end, once you have finished the model training, in the end, if you see, it will dump certain outputs. It is saying that it has created the profiling output and it is present in a particular location. The location is kind of listed here, which is nsys profile.sqlite database, and it also stores it in another database called as qdrep file, right? Not just that, in fact, in the end, it will throw out, after you have trained your model, it will throw certain issues. If you read the issues are kind of highlighted. What it is saying is, I have detected 5 issues, and note that the experts system is still experimental, and these are hints given to you, and you can check whether it is doing certain things or not. Is it doing XLA or not? And you have done a session where we were talking about XLA, but let me show you the last session. There was a particular lecture on AMP, whether automatic mixed precision you can use or not. So you can see here that it is telling that you are eligible, 10 operations were eligible for Tensor Core, and it can use FP16 using automated mixed precision, but we have not enabled it. So you can improve the accuracy, or you can improve the performance or the overall throughput by enabling mixed precision. Try doing that. It is one of the problems. Another thing it has listed is that we observed that there are 8 GPUs on your system and you utilize only one of them, which is GPU ID 0, while 1 to 7 are not being utilized. So ideally, you should look at distributing your work, right? And there are many more things. Another problem that it is highlighting is, with the current batch size, the GPU is underutilized. It is only utilizing 31% of the GPU memory. So you can actually increase the throughput of your system by 2 times by changing the batch size. So you can see here, by running it via profilers, you can actually get much more details of your system, right, of your overall thing. And now that's what is very, very critical to understand, right? So the profiler can give you more details without you having to know about it. We can also visualize it in form of much more detail. So what I'm going to do is that I'm going to open new terminal, file new terminal, and I'm going to run a particular command as a server so that I can visualize the details. I'm going to say dlprof weaver -v, dlprof weaver -v 0.0.0.0, and then -p 8000. So I'm opening it at a port 8000 so that I can visualize that port 8000. And then I'm just looking at Python notebook of one, and I want to visualize the profile input which was created just now. So let me just run it. And I'm going to open now the another terminal and visualize my output using not just command line, but also the via a visualization tool. So you can see here the DLProf, whatever it showed on the command line, you can actually see it inside a visualization tool. It's like a client server model. So you can see here, when I ran my system, it is saying my GPU is only utilized actually for this much of time in my overall simulation. You can see here it is telling me that I am actually running it only, the GPU is only utilized for this much of time, rest all it is idle, it is not doing anything. And it is also telling me that I am, whether I am using tensor cores or I am not using tensor cores, how much time I'm using the CPU and how much time I'm not doing anything or I am just waiting. So you can see here that actually I'm not doing a very good job at it. The total kernel time spent on the tensor core is almost none. So I'm not using any kind of a tensor core operation, right? And also it does, you can see it in different forms in terms of iterations and all, like for every iteration, how much duration was spent and much more than that. It also highlights the part of how to use different features, like how to use, say, automated mixed precision, and it also has linked to the definition of what, how you can enable it, or what is the definition of automated mixed precision. So you can enable it and click on it and get more information about automated mixed precision. This is like one of the view, which is a dashboard view. You have other kinds of view as well, like operation types. So I was showing you one of the views of dashboard, and now we have another view which is op type summary. This is much more detailed view, which gives you different types of operations which are done in your network and how much time is spent where. So you can see here it is telling there's an operation which is called as convolution 2D backpropagation, convolution 2D backpropagation of different type. You are also doing ReLU, you are doing matrix multiplication, you are doing max pooling. And it tells you for each and every operation how much time was actually spent in the CPU time and how much time was spent on the GPU. So you can give that view also. You can go via, there are different things here, right? You can go to the GPU view, and there you would be able to see how much utilization is there for every GPU. As I told you that we are utilizing only one GPU, while rest all GPUs are not even utilized. In fact, the GPU 0 itself utilized only for 30%. Right? And that's what can be seen via this DL profiler, which can give you very, very good insights into your existing utilization of the GPU itself, right? So we can get more and more details about each and every operation, each and every GPU, and it will give you all those statistics. So that is what is DLProf all about. So you can utilize the DL profiling tools to make sure that you are getting really good really good insights into whether you're utilizing your overall system also efficiently or not. So in this particular case, what we were trying to do was to do the same thing, that we can run the same using, say, 0 and 3 GPU using Horvath, and 1 and 7, and run the same task which we were running some time back. And you would observe that when you do that and when you run via DLProf, you would see that when I use GPU 0 and 3, the average time which is spent on the GPU is 256 nanoseconds. So it is showing, if it is not visible, let me just increase the resolution. You can see here it says 256 nanoseconds. While if I use 1 and 7, it shows that the time spent in the GPU is actually higher, which is 500 nanoseconds, which you might feel I am spending more time in GPU is good. Actually, it is not, because the NCCL communication times are actually increasing, and hence you are spending more time. So ideally, the time should be reducing and not increasing, and that's what can be utilized. And you can see here, I'm specifically selecting that I want to see only NCCL time. So you can see here that the NCCL time, which is the communication time on the GPU, got doubled when I ran from 0 to 3 to 1 to 7, because 0 to 3 NVLink is there, 1 to 7 NVLink is not there. So NCCL actually ends up spending more time on the GPU, reducing your overall scaling. And you can basically do the same experiment. Now here in this particular case, what we are doing is we are intentionally removing peer-to-peer transfer and doing the same thing, and you will end up seeing the same statistic. By you can enable and disable peer-to-peer on your own, right? So we can see different stats and you will be able to get the same stuff. Another very quick thing I wanted to show you with respect to your system. Now, if you have a system and you don't want to get bottleneck by running these kinds of tests, there are open source benchmarks which are available for you to do testings. Like here in this particular case, I'm using a benchmark which is called as peer-to-peer bandwidth latency test. So I'm compiling that benchmark right now, and I'm going to run this test, and I'm going to explain it to you what this test can actually do. The test, first of all, will show you whether peer-to-peer can be enabled or not enabled, but more importantly, it's going to show you certain metrics. Here you can see it's telling when I disable peer-to-peer, how much bandwidth I can achieve across different GPUs. So you can see here when I do a bandwidth test between GPU 0 and GPU 1, the bandwidth I'm getting is only 9.41 in case I disable peer-to-peer. But if I enable peer-to-peer, in that case, my bandwidth increases from 9.41 Gbps to 24 Gbps. Same thing between GPU 0 and GPU 3. If I enable peer-to-peer, it increases because I have double NVLink, it increases to 48 Gbps. So you can run some of this test and you can find out those things. And we are almost at the end where we are talking about why running peer-to-peer. You can see here, you can also observe that the latency, if you disable the peer-to-peer versus if you enable the peer-to-peer. If you disable, if you don't have peer-to-peer, it is taking much more time, like 17 user seconds to reach between GPU 0 to GPU 1. But if the peer-to-peer is enabled, it only takes 1.62 user seconds, which is quite good. So in short, what I showed you is a couple of things today. What we did was we actually used Horoword and TensorFlow to run it across multiple GPUs. We also showed you the impact of network topology, how you can find those network topology, and also you can basically find out uh, uh, in more details by using certain of these profiling tools. Tomorrow, we are going to go into more details of how to utilize or how to use different frameworks and get into more details of running it on TensorFlow as well as on Horoword. And also we are going to cover some of the parts of what kind of challenges can come our way or with respect to conversions when you have different size of batch or when you run it across different say number of GPUs, and you might have to change your conversion strategy or your adaptive strategy in terms of say what kind of a method you use for back propagation. And we are going to cover that into more details in the tomorrow's session.